Welcome, I'm Mr. Kimball and this is your
Flipped Classroom. Hi, welcome back. Today we're going to talk about the basics of physics. So we're going to cover things like measurements, uncertainty, do some unit conversions, scientific notation, significant digits, and dimensional analysis. So the first thing we're going to talk about is measurements in physics. Measurements in physics are based on standard units of time, length, or sometimes distance or change in position and mass. Quantities, the units, the abbreviations, and the variables. These are all very different things, and you need to be careful about exactly what it is you're looking at. So your quantity, the name of what it is that you're doing. So time, length, etc. Unit. This is thing that you're measuring time in. So the unit that we're talking about, that is the actual thing that you're measuring. It's usually a standard unit, the SI units, and there's different variations of that, and there's some prefixes that go along with it. So your kilometer, your gram, your milligram, those types of things, those are all units. The abbreviation is actually what I just gave you. So, a second, things that you might not understand is, a Newton is a unit of measurement. For force, its abbreviation is N. So those are the abbreviations, and the reason I bring those up is because your abbreviation is not the variable. The variable is how it looks in an equation. So this is T for time, or length for L, and so the variables are what you find in an equation. The units are how you are going to measure that thing, and so you've kind of got what it is that you're measuring. Okay, so I'm going to measure length. The unit is going to be based on the instrument that you're using, so maybe a meter or millimeter, kind of depend on the tool you have. And then the variable is how we will abbreviate the quantity in the formula. So they're all a little bit different. Okay, this chart here kind of displays some quantities and units, and this next chart will display all the different types of units that are out there. We'll come across a whole bunch of them. We'll kind of cover them as they come up. Unit conversions. Unit conversions help. Unit conversions help us change from one type of unit to another type of unit. Okay, we use what's called an equality. Everybody knows that 1 minute is equal to 60 seconds. Okay, that is an equality, and you'll notice that I have a unit of time and a different unit of time. Okay, and so we can use these equalities by setting this thing equal to 1 and then plugging 1 anywhere that we need to change units from one to the other. Okay, and so what we do is, so if I divide both sides by 60, I have an equality that 1 minute is equal to 60 seconds, right? And I could have done it the other way, and that's still equal to 1. And so what we see with these equalities is that I can stack this thing, and then I can use it in either way. Okay, it doesn't do me a whole lot of good in this form right here. So what we'll do is we'll convert it into this, so that this whole thing is equal to 1, and then depending on how I want to use it, which units I want to change it to, I'll plug those in. So let's say I want to know how many minutes are in 400 seconds. So I collected some data, I have this big number, 400 seconds, that doesn't make a whole lot of sense to me. I want to put it in terms of minutes so I can understand it better. And so I'm dealing with seconds and minutes, and so I have to choose my inequality. And so I know that there are 60 seconds in 1 minute, okay? And I don't know which way I want to do that, and so I go over here and I say, what am I in and where am I going? So I'm going to say I am at 400 seconds. And what I'm going to do is I'm going to multiply that by something to get it into minutes. And so if I want seconds to cancel out, I'm going to want these seconds over here in this this equality. I want that to be on the bottom so that they cancel out, because you know that secretly this guy is over 1, right? And so I want to put seconds on the bottom and minutes on the top. And so I know that there's 1 minute in 60 seconds. My seconds will cancel, and my unit that I'll have left is minutes, which is what I want. Now I do the math. 400 times 1 over 60, the same as 400 divided by 60. And if you did that math, you would come up with 6.67 minutes. And to me, that makes more sense than 400 seconds. I can relate to this, and that might be why I want to do that. We got to do a few things. My time increment has changed, and my distance or my length has changed. And so I'm going to do several parts. So I start out with what I have, 47 meters. I'm going to write this a little bit differently in 1 second. That'll help me see the tops and the bottoms, and we'll do train tracks this time. And then the only thing you have to do now is you're going to multiply across the top. So you're going to multiply across the bottom, and then you'll divide those two numbers, 105 miles per hour. We in physics deal with really large numbers and really small numbers. Okay? So the way we deal with this is scientific notation. So scientific notation, or sci note, is when you write the number with a single integer between 1 and 10 with a decimal and a times 10 to some power n. Okay? So let's do an example. Dealing with a really large number, the distance between planetary objects, okay? The Earth and the Sun have a distance between them of 1 astronomical unit. And it's called 1 AU. You'll see that every now and then. It's a standard unit for astronomy. That's equal to about 150 million kilometers. Okay, and that's a really big number, and if you were dealing with a whole bunch of astrophysics and math out there with large numbers, you're not going to want to carry around all of these zeros. It's going to be a pain in the butt. And so what I want to do is change this into scientific notation. Okay, I want to change it so that this number is between 1 and 10. And so the best way to do that is you're going to go 1.5. I'm going to take all those numbers and I'm going to make it equal to 1.5. And then what do you do with these zeros? Okay. Well, what you're really doing with this is you're multiplying it by a power of 10. In layman's, in middle school, what we typically say is we just count where the decimal is. You know that there's a decimal over here, and I'm going to move it to the left. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8 times that way. And so basically what I'm doing is I'm multiplying this 15 million by, or I'm sorry, I should say dividing it by a power of 10 to the 8. So these are the same number. This one's written in scientific notation. And in order to go from this to the scientific notation, I divided it by a power of 10 to the 8. So if you see something in scientific notation, what that means is that you are multiplying it by a power of 8. And so roughly speaking, if it's a positive integer, positive exponent, you're going to move the decimal to the right that number of times. And so I bounce it 1, 2, 3. And you can undo that, right? If it's a negative exponent, you're going to go to the opposite side. And what that's saying is, to unpack this, is you're going to divide it by that power, because 10 to the positive 8 is all up here in the numerator, but if I changed it to times 10 to the negative 8, what that really means is that that power is in the denominator, and so I would divide 1.5 by 10 to the power of 8, and that would unpack this number. Okay, I would move the decimal this way, right, and make it a really, really small number. Okay, so if the exponent's a negative, you're going to move that decimal to the left, which basically you're dividing it, or if it's a positive number, like in this example, you're going to move the decimal to the right, which means you're multiplying it. You're making it a bigger number. Okay, so scientific notation is used to deal with really large, really small numbers. And there are some of them that are really common. So let's do another example about some common ones. Okay, some of the really, really common ones, we have a prefix chart. Let's take like a power generator, okay, a power station of energy per hour, right? That's a ton of energy. But again, it's so much energy that I don't want to deal with all of these zeros. So how do I take care of that? Well, let's put that into scientific notation. And that's fine. You're done, okay? If you were using watts and you wanted to use scientific notation, that's perfectly fine. But I know, if I look at this prefix chart, that 1 times 10 to the 9 is a giga. Okay? So we could call this a gigawatt. And so what I do is I substitute that for the G, and I can just say it's 1 gigawatt. So these are all equal. Sig figs, as they're commonly called. These account. So significant figures are really important to understand. We will use them off and on in class. If you're an AP student watching this, we're going to need to get very familiar with these because the AP test loves sig figs. Okay, but the general idea of significant digits or sig figs is that they account for the uncertainty in measurements, and they can reduce compound errors that would develop as you multiply or divide or add or subtract multiple numbers that you've measured. So if you're measuring, say, the length of a nail, I'm measuring the length of a nail. I put my ruler up to this nail, and you'll notice that it's in millimeters. That's important, that's a unit. And you would notice that the nail head lines up somewhere between 15 and 16. Now, my ruler is only precise enough to measure to the nearest whole millimeter, right? But I have keen eyes. I'm a good scientist. I can definitely tell that that nail comes between almost exactly 15 and 16. And so I feel comfortable in estimating this nail to be 15.5 millimeters long. Okay? That would be an acceptable error, right? Now, could I say that this nail is 15.47 millimeters? Man, I don't know that my eyes are that good, that I'm I don't even remember what that is. I can't see that, okay? When I take a measurement, I know that that last number is an estimate because I was trained to go to the nearest half, exactly half in between them, and just take the best guess. But I know that there's some uncertainty in there. It could be 15.4. It could be 15.6, you know? And what we're doing is we're kind of limiting my uncertainty with the significant figures. And so you know that this nail has 3 significant figures. It does not have 4 significant figures because I can't really see that 0.47. Okay? The more sig figs that you have, the more precise your measurement. The diameter of our moon, Luna, is known to a certainty of plus or minus 1 kilometer. Now, after doing some measurements, I found that the moon was 3,476,000 meters in diameter. Now, this number here, because of our uncertainty, is an estimate. So it could be 477, 475, I don't know. Okay? It really doesn't matter at all what these numbers are, plus or minus 1 or 2 or 50 or whatever it is, because I'm estimating out here in the thousands. Okay? Nobody cares about 50 meters if I can't nail down the thousands. Okay? So understanding that this is an estimate, we would say that this has 4 significant figures. Okay? Now there's another moon further out named Hoya. So a much less, we should say a less good tolerance or less precise measurement. Okay. Now it's very far away, it's very small, it's dark, it's hard to take a measurement, so that's understandable. Now when we took measurements of it, we found that it was 460 kilometers in diameter. But because I have an uncertainty of plus or minus 10 kilometers, I don't really know what that number is. Okay, so because of this, I only have 2 significant figures here. So this could be 450 kilometers in diameter, it could be 470 kilometers in diameter. I have a lot less certainty. Okay, now it's important to note that the units itself is not really causing the uncertainty. It's the measurement. It's the tool we're using and the circumstances in which we're measuring it. Because this 460 kilometers is 460,000 meters. Now I'm still estimating at this digit, I still only have 2 significant figures. So it's important to understand it's not the units, it's the tool you're using that is minimizing or maximizing your precision. So a more expensive tool, a more precise tool will give you more sig figs or significant digits. Okay, now the reason sig figs are such a pain to everybody and they always hate them is because every time you open a textbook and you try and understand significant digits, every single textbook is going to lay it out a little bit different. We're going to go with these rules. Number 1, leading zeros are not significant. For example, 0.0035 has 2 sig figs. Trailing zeros to the right of a decimal are sig. If there's no decimal, trailing zeros are not significant. 0.3500 has 4 significant figures. 350, there's no decimal, has 2 significant figures. If I were to put a decimal, then we're back to 4 zeros, or 3 zeros, and you don't often see that written there. Okay? The reason you don't often see that written there is because a lot of times what people are doing is they're saying that there's 60 minutes in 1 hour. Okay? That's a quantized number. I know that there are exactly 60 minutes because I counted each minute. That has 2 significant figures. So unfortunately, it's a little bit ambiguous, but unless you are counting something, trailing zeros to the right of a decimal are significant. If there's no decimal, they are not significant. Okay? So they're kind of like part of the same. Alright, I know it's not the best. 43.9 divided by 2.3 seconds. This one has 3 significant figures. This one has 2 significant figures. When you do the math, you get 19.086996, etc. Right? You get this huge long number. But you're not going to want to use that whole number because the 2.3 seconds is your significant number because it's the least amount. There's only 2, and so I have to report my number as 19 meters per second. Adding and subtracting, you're going to use the least amount of sig figs after the decimal. If I had 44.3 kilometers and I was going to add that to 0.108 kilometers, this one has 3 sig figs overall. This one has, because the leading zero is not significant, it has 3 sig figs overall, okay? But you're going to report your answer with 1 sig fig after the decimal, okay? So when you add these things up, you get, and I need to keep this last 1 sig fig after the decimal, and so that's where it's going to stop. So I would report my number as 44.4 kilometers. Sig figs are not easy. We won't use them a ton, but you need to be aware of them, and especially in the labs, I want you to try to apply these, especially you AP students, because it will be expected of you on the AP tests. Dimensional analysis. This is a powerful way to check the results of a calculation or to derive other versions of equations if the equation that's been given to you doesn't work for you. We see this a lot when we deal with velocity, acceleration, displacement, kinematics. We will use dimensional analysis to come up with new equations because my experiment might not be able to get all the data I need to use the appropriate equations. And so I can substitute known quantities and make things work out because of the equalities. Okay, so in an equation, the dimensions or the units must be the same on both sides of the equation. Okay, the time it takes a ball to fall from a certain height might be expressed as h equals vt squared. So if I draw a picture here, I got velocity times squared is equal to h. Okay, so this is kind of what's going on. I'm trying to figure out the height and the velocity and time and all this stuff that's going on in this experiment. I start with this equation and let's see if it works. Okay, first thing I'm going to do is I'm going to plug in the units for each variable of the quantities that I know. So height is going to be in meters, velocity is meters per second, time is in seconds, and they squared it. And it's not explicitly said, but I know that that seconds is over 1, okay, because it's in the numerator. Okay, now when I simplify, okay, I can divide that s squared over to the other side, and so I've got ms squared is equal to m over s. The dimensions, the units, meters per second squared, that's an acceleration, is not the same as meters per second, that's a velocity. That is not a true statement. Okay, so h equals vt squared will not explain how this ball is falling. Okay, that doesn't work. What we find is that the height can be expressed using the acceleration of gravity that's an acceleration. Okay, let's check. Height meters. I'm going to ignore all these numbers or these constants. G, which is an acceleration, is going to be meters per second squared times t squared, which is second squared over 1. When I divide it over, I get meters per second squared is equal to meters per second squared. That works. That equality is good. Okay? And so the formula h equals 1/2 gt squared would explain this scenario. H equals vt squared would not. Okay? That, what we just did is we analyzed the equations using the dimensions. Okay? Or dimensional analysis. That's what we did. That will be applied on your own to check your work. It will also be applied when we start to think about what's actually going on. The reason this one works and this one doesn't, this is saying that the ball is falling at the same constant speed the entire time. You probably know this, and if you don't, we'll talk about it, but there's a force pulling things towards the center of the earth, and it's a constant force. Even force is causing an acceleration. So that ball is actually falling not at a single speed. It's falling and it's getting faster and faster and faster and faster. It's accelerating. And it's accelerating due to that Earth's gravity. So this equation makes a whole lot more sense.